Hello, we're back to talk about the rest of chapter 5. So in this video, I'm going to talk about the rest of chapter 5 if you have time. I'm going to talk about rational functions and then these two sections here, and if we get to it, I'm going to talk about them. But let us start. So I'm going to get rid of my video, we don't need it. And first let's talk about rational functions. What are rational functions? So let's look at some examples, and then we're gonna go to that section in the text and talk about it. But for now, what is a rational function? Well, you know that polynomials are a polynomial. We already talked about polynomial. It looks like this, right? And the graph of polynomials are smooth and continuous. So they have what? They have no breaks. So you don't see anything like, for example, you don't see the graph approaching a line but never crossing it. Such a line is called a vertical asymptote, and polynomials don't have that because they're continuous everywhere, right, for all real numbers. So you don't see anything like this. So the graph comes to a line and then goes up, or maybe comes down and approaches the line but never crosses it. Or you don't see anything like this. When we have a line, a straight line, and then the graph approaches this line, it might actually crosses it. It might cross it. Maybe it crosses it again, right? But eventually it's going to approach this line. So if you go to infinity, you see this line, right, is approaching this, getting closer and closer to this line. Now between, like in around 0, maybe close here, that is not at infinity, the function, the graph might cross the line, the horizontal line. So this is called a horizontal asymptote. So asymptote is named because the behavior at infinity is called asymptotic behavior. So when x approaches infinity, we want to know what the function does, and that is asymptotic behavior. So on the left, it doesn't have to, maybe it looks like that, but on the right, it approaches it. It could also be that, there is two of these actually mixed. Maybe there is a vertical that the function approaches, and here maybe it's going to behave like this. So we have graphs that are like this that are not obviously graphs of polynomials, right? You could also have a situation where you have a graph, but in the graph there is a hole like this. So we might have a graph and there is a hole, let's say some number 3 here. So this function is defined everywhere except at 3. So this is not a polynomial either, because polynomials defined for all real numbers. All right, now you could also have lines that are slanted like that. So we might have a situation where the graph of a function, maybe we have two of these mixed, like one of these and one of these. And the graph maybe does something like this, right? So these are all situations where with polynomials we didn't have these situations, maybe something like that, right? So these kinds of graphs, obviously they're not polynomials, right? You could also have situation when we have another polynomial, maybe is a line, and then the function approaches it, something like that. So all of these are not graphs of polynomials. So how do we get all these? So what I'm going to do, I'm going to do this so I don't have to erase all that. So now let's talk about when we get weird graphs like that. So we get graphs like that if we have a situation where we are dividing two polynomials. So p of x divided by q of x. So remember, p of x is a polynomial, so we're going to write it like a sub n x to n plus dot 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 plus a sub 0, and well, the denominator, I have to use different letters for the coefficients, and I'm going to also use different letter for the degree, because it might be a different degree, right? So that would be a b sub 0 here. Okay, all right. So if we have a situation like this, a function that is a polynomial divided by a polynomial, then we have something called rational function. So these are called rational, from ratio, right, functions. So rational functions. So rational functions are basically polynomial over polynomial. That's rational function. So let's look at some examples. So what do you think this is going to look like? Like, let's say x plus 2 divided by x minus 1, right? Well, this is going to have problems when x equals to 1, right? When x equals to 1, this is going to have a problem. So this is going to have one of those lines at 1 where the function cannot what? Cannot cross. So the graph of this obviously is going to be broken into two parts, to the right of this and to the left of this, right? And we're going to get to graphing these, but for now, that's how we can get those weird graphs. So if there is an expression here that makes the denominator 0, then those values that make the denominator 0 will create what? Vertical asymptotes. So we're going to write here that r of x, when I say r of x, I mean what? This. So r of x has vertical asymptote at x values that make q of x 0, but not p of x. So what does that mean? That means if you have a situation where x value makes numerator and denominator 0, then we have a situation that is called 0 over 0, and this is indeterminate. That means we don't know what this is. We don't know. This could be, any number, 0 over 0. It would mean that there are two factors, one in the numerator and one in the denominator, that make this function 0 over 0. That means if we cancel that factor, we might actually get something. So that doesn't mean undefined. If the denominator only is 0 and the numerator is a number, then the function has vertical asymptote at those values, but not if 0 over 0. I'm going to talk about what we have if we get 0 over 0. But for now, we have vertical asymptote only when what? When the denominator is 0, and I gave you an example for that. Now, so we say r of x has x-intercept at x values. When we say x values, of course, they have to be in the domain. At x values, so if we get x values here that make the denominator 0, we're going to take them out of the domain, right? So if we find x values, r of x has x-intercept at x value it could be intercepts, could be more than one, at x values that make p of x 0, but not what? Q of x. So what does that mean? That means, for example, here, this has x-intercept at, how do we know? We set the numerator equal to 0, at x equal to -2, right? So you see, this function has one vertical asymptote at 1, right? And has an x-intercept at -2. So if we were to graph this, that's how we start, right? All right, what else do we know about rational functions? Well, we know that r of x has a hole at x value that, or we can say has actually holes, so we can make it plural, holes at x values that make p of x and q of x 0. Okay, so we don't have that here, but we can make one. So let me give you an example that is like the third one. So here is an example in a situation like, so let's see. So I'm going to give you this example. X to the third minus 1 divided by x minus 1. Now, you might say, well, we have a vertical asymptote at 1, but we don't. Why? Because vertical asymptote has to make this 0, but not that. So x equals to 1 is not a vertical asymptote. Is it an x-intercept? No, because it makes the numerator 0 and the denominator. So it's not an x-intercept. But what happens at 1? Well, at 1, what we're going to have is going to be a hole. But where is the hole? Well, to find the hole, we have to factor what numerator and denominator have in common, and we know what that is. We can actually divide this. Remember, we know how to divide. So let's divide it using synthetic division. So what do I put here for the dividend? 1. X squared is not there, so I have to put 0. X is not there, so I have to put another 0, and then -1. And I want to set this equal to 0 to find the root of the denominator, which is 1, and we'll put it here, right? And then what? Then we bring the 1 down here. 1 times 1 is 1. 1 plus 0 is 1. 1 times 1 is 1. 1 plus 0 is 1. 1 times 1 is 1. 1 plus -1 is 0. And now we know, because this is third degree, this is 1x squared plus 1x plus 1. So that is the quotient, and the remainder is 0. So that means we can write this as what? As x minus 1 times x squared plus x plus 1. And then over x minus 1. Now these two cancel. Now notice that what we have now is just what? X squared plus x plus 1. Which looks like is just a polynomial, but is not. It's actually a rational function that comes from here. We simplified it, but we have to put here what? X, we put comma. X cannot be what? 1. So basically it's going to look like x squared plus x plus 1, but it doesn't have any point at 1. So what does it have at 1? Well, what is the y coordinate at 1? Because we have a hole has to have x coordinate and y coordinate. So we know the x coordinate of the hole in this graph, which is 1. So the y coordinate comes from this simplified expression after you cancel what they have in common. So if I put a 1 here, 1 squared is 1 plus 1 is 2 plus 1 is 3. So 1, 2, 3. There's a whole here, right? So this is r of x. And then if you graph it, you're going to see what? A parabola that opens up, right? Where is the vertex of this? Well, the vertex is at negative b over 2a. So b is negative 1 over 2 times 1 is negative 1/2, right? So negative 1/2, which is about right here. That's negative 1/2. That's the x coordinate of it. Where is the y coordinate? Well, we have to put negative 1/2 in here to find the y coordinate. So negative 1/2 squared. So negative 1/2 squared plus 1/2 plus 1. So negative 1/2 squared is just 1/4, right? And then this is what? 1 plus 1/2 is 3/2. So 3/2 plus 1/4, if you multiply these by 2, we get 6 over 4 plus 1 over 4 is 7 over 4. And 7 over 4 is like 2 point something, 1 point something. So it's about right here somewhere. That's the vertex, right? Now the y-intercept of this is 1, so it goes through 1 here, and then that way, and then we have a hole, and the rest of this, of course, looks like this. So you see, that's the graph of this rational function, right? It doesn't have vertical asymptote. It doesn't have any horizontal asymptote. It has a hole, and we found the hole, right? All right. Now we want to let me continue with properties of rational functions. Then we're going to apply all these and do some more examples. So far we talked about vertical asymptote, x-intercept, holes, right? What other features can they have? Well, another feature they can have, I already talked about, that is the horizontal lines. Remember those? So think about horizontally. What do we? How do we get those? This is taking long. That's okay. Here you go. I got this. All right. Finally, we got all of those. So let's think about a rational function. For example, I'm going to give you 3 of them. Let's say 2x squared minus x plus 1 over, let's say, 3x squared plus 2x minus 5. Then I'm going to give you another one. R of x equals to 3x minus 1 divided by 2x squared minus x plus 3. Then I'm going to give you another one. 3x to the third minus 1 divided by, let's say, x squared plus 3 plus 1. Something like that, okay? Now, what we want to look at is end behavior of rational functions. What happens if x goes to infinity from right and left? Well, when x goes to the infinity from right and left, the way that we look at this is we're going to think of this when x is really large just as what? As 2x squared over 3x squared. So the leading coefficient divided by leading coefficient. And this is going to determine the end behavior. So when x goes to infinity, this is x squared and this is x squared. So both of them basically have the same size, infinity squared. So you can think of they don't contribute anything because whatever it contributes in the numerator, this one in the denominator cancels it, right? So we are left with just 2 over 3. So what does that mean, that the end behavior is 2 over 3? Well, it means this. I want to put it here. So we say R of x has a horizontal asymptote, which is given by y equals to a sub n over b sub m if n equals to m. So basically what we are saying is that if the denominator and numerator have the same degree, the polynomials have the same degrees, then y equals to a sub n over b sub n is the horizontal asymptote. So in this case, horizontal asymptote is y equals to 2 over 3. And this one, what about this one? Well, this one is approximately 3x over what? 2x squared. Now in this case, when x goes to infinity, this is infinity, but this is infinity squared. So this is much bigger than that as x gets larger and larger. So we end up with really a huge number in the denominator and much smaller number in the numerator. Something like, let's say 200 over 10,000, something like that. And then as x gets bigger and bigger, this becomes much bigger compared to that one. This becomes bigger too, but not as much as this one. So eventually what happens is this whole fraction goes to 0. So what we're going to say is this. We're going to say that if R of x has a horizontal asymptote given by y equals to 0, if n is smaller than m. That means degree of the numerator is smaller than denominator. Then y equal to 0 is a horizontal asymptote. And if the degree of the numerator is bigger than denominator, R of x has no horizontal asymptote if n is greater than m. Now in this case, we're going to talk about this a little bit more later, but for now we know horizontal asymptote will be what? No horizontal asymptote if the degree of the numerator is bigger than denominator. Now what are we going to have if the degree of the numerator is bigger than the denominator? So what happens at infinity for this function? Well, what happens is this. You're going to get one of these. Either we get that, a line, a slanted line, or we get a quadratic, or we get a cubic, and so forth. So the behavior of R of x is going to look like a polynomial, basically. Now, how do we get a line is if the degree of the numerator is 1 more than the degree of the denominator. So that means n equals to m plus 1. Then you get a line. If n equals to m plus 2, you get one of these. If n equals to m plus 3, you get one of these, and so forth. We're going to just talk about this one. We call it the slant asymptote. Again, the only asymptote that the function cannot cross is the vertical asymptote. Vertical asymptote the function cannot cross. But the horizontal asymptote or any of these can be crossed by the function many times and then approach, right? Even these, they could be cross and then approach, right? So you can cross and they approach. Okay? All right, so we're going to talk more about this and how to get them. But for now, let me just say what happens here. So in general, for this one, to get the asymptote, you divide the numerator by the denominator, long division. And we know how to do that, right? And we get some expression here. Whatever expression we get here, we don't care about the remainder. Don't worry about the remainder. We just do it until we get something we can't continue anymore. Then this right here, y equals to that, whatever that is the equation of that line. And the same thing is what? For if n is, 2 more than m. The same thing. We divide the numerator by the denominator, right? Whatever the numerator and denominator are, we divide them. Whatever we get here is the equation of that. The same is true here. So basically, to get the asymptote, what type of asymptote we have, we just divide the numerator by the denominator, and we take the quotient. Y equals to the quotient is the answer. All right, so let's just start doing some examples. So let's go to this section here. It says for the following, I'm going to do number 7 and 9. So what do we have to do? It says for the following, find the domain of the rational functions. Okay, so let's find the domain of both of these rational functions. There we go. So domain would be, basically domain of the rational functions are all real numbers except those that what? Make the denominator 0. So you can write the domain is a set of x values such that what should be true? Well, we put the condition that x plus 2 cannot be what? Cannot be 0. So we set it equal to 0 to figure out what makes it 0. Then we say, okay, domain is all real numbers except x cannot be what? Negative 2. You could also write it on the number line. Just this is negative 2. We don't want that, but everything else is good, right? So what do? We say from negative infinity to negative 2, union from negative 2 to infinity. So that's the domain of this function. This is number line form, which we don't really use in textbooks. We don't use that. We use this or we use this. This is interval notation, and that is set builder notation. Okay, what about this one? Well, the same thing. Domain of this one would be all real numbers except what? Except what makes x squared minus 1 0. So what makes that 0? Well, we know what makes that 0. X squared equals to 1. X is plus and minus 1. So here we say x cannot be what? Plus and minus 1. That's it. Okay? All right. Now let's do number. And over here, before I do that, vertical asymptote for this would be x equal to negative 2. Vertical asymptote for this one would be 2 vertical asymptotes. So let me actually graph these just to get a feel of these things actually look like with our program right here, right? So what I'm going to do, I'm going to put y equals to, I put parentheses for the numerator divided by parentheses for the denominator. So in the numerator I have x minus 1, and in the denominator I have what? X plus 2. And notice here that this graph has what? Has a vertical asymptote. If you put y equals to negative 2, I meant to say x, but I put y. So let me delete and do it again. So x equals to negative 2. And then what I'm going to do, I'm going to make it red and dotted. So you can see the difference. Let's make it a dotted line. Okay, so now that you see, this graph is approaching but never crosses it. Now also, we said that if the degree of the numerator is the same as denominator, then what do we have? We have horizontal asymptote, which is y equals to 1 over 1, right? Because they're the same. The leading coefficient of the numerator is 1, and the leading coefficient of denominator is 1. So y equals to 1 over 1, which is just 1. So y equals to 1. And again, we do the same thing here to make it what? Red and dotted, okay? Let's get rid of that. So notice that as you go to infinity, see, close to 0, this is what's going on. And x-intercept, of course, is x minus 1 equals to 0, so it's x equals to 1, which is right there. But here what I want you to see, if I go to the right to infinity, you see what happens? Well, this is approaching what? This line, and it gets closer and closer. And if you go to the left, the same thing happens. You see that? It gets closer and closer to that line, okay? Now, so the vertical asymptote is x equal to -2. Horizontal asymptote is y equals to 1, right? Now, one question that we like to answer, that I'm going to talk about right now, is whether this function, so let me get this area so I can write on it. So the question is whether this function crosses its own horizontal asymptote while you're not looking up there somewhere, right? How do we know it doesn't do that? Well, what we can do is we can set these two equal to each other. So we're going to set the function, which is x minus 1 over x plus 2, equal to its own what? Asymptote, which is 1. And then cross multiply, so x plus 2 is going to equal to x minus 1. Then if you move the x's to one side and move the numbers to one side, what do you end up with? 0 equals to -3. What does that tell us? That there is no what? No solution. What does that mean? Well, it means that this graph will not cross this red line, ever. That's how we know. Okay. All right. So what about the, so let me move this down so we can use it again. So I'm going to do maybe one more. What about number 9? There you go. So for number 9, let me move my microphone down so a little bit. All right, so so we have to figure out what makes the denominator 0. So what do we have to do? We have to set it equal to 0, as you see over here. Now, this, if you think about this, this is called quadratic in form, and we talked about this in previous chapters. But if you have something like that, you can think of it as, think of this as m. So you have -5m plus 4. And if x squared is m, then x to the 4th power is like m squared, right? You can think of it like that. So we can factor this. This is what? This is m. What is m? What? Two numbers multiply, you get +4, and you add, you get -5. So it looks like that. So you know what m was? M was x squared. So this is really x squared minus 1 times what? X squared minus 4, right? So it said that equal to 0. That means either this equals to that or this equals to that. So x squared minus 1 equals to 0. That means x is plus and minus 1. And then x squared minus 4 equals to 0. So x is plus and minus 2, right? Move and take square root of both sides. So we got 4 numbers that don't belong in the domain, right? So what do? Well, we're going to write domain is x such that x is not what? Plus and minus 1 comma plus and minus negative 2. You can write it like that, that's fine. But if you want to use an interval notation, that would be many intervals, right? Starting from negative 2, right? And then you have negative 1, then you have 1, and then you have 2. So you don't want any of these. So you're going to have 1, 2, 3, 4, 5 intervals with the union, right? That's how you write it. But you can write it this way, it's easier. Alright, so that's the domain for that function. Now, what about, let's see, number 10. It says, for the following, find the domain, vertical asymptotes, and horizontal asymptotes. Okay, so let's do that. Now, sometimes the rational functions are related to these functions. 1 over x, 1 over x squared, right? We know how to graph these. So 1 over x looks like this, right? So vertical asymptote is where is actually y-axis, because 0 makes the denominator 0, right? So whenever we have something like this, we can think of this as what? As one of these and use transformations, right? So how do we get this out of that? Well, we can start with 1 over x and subtract 1. That means what? Is a horizontal shift to the right, and then multiply by 4, which is a vertical stretch, right? So to get the graph of this out of here, we just have to what? Move it to the right, 1, and then vertically stretch it, right? But we get to that. But for now, let's talk about what? The asymptotes. Alright, so what is the vertical asymptote? So vertical asymptote is going to be, we said x minus 1 equal to 0. We say x equals to 1, right? Horizontal asymptote, where the numerator's degree is 0, denominator is 1. So this has a horizontal asymptote, y equals to what? 0, right? And that's it. So vertical asymptote is x equals to 1, and horizontal asymptote is y equals to 0, right? So basically means that if you want to graph this, so vertical asymptote is x equals to 1, should be this line, and the horizontal asymptote is just the x-axis itself, right? Now, does it cross its own asymptote? Let's see. This is 0, this is 4 over x minus 1. So if you set that equal to its own asymptote, right? What do we get? Well, this is not possible, because if you cross multiply, you get 4 equals to 0. And no solution, right? That means it doesn't cross its own horizontal asymptote. We know it never crosses vertical asymptote, because that would mean what? That x equal, denominator equal to 0, and you have a fraction with the denominator of 0, and you have a value if it crosses, and that's not possible. Okay, so how do we graph it? Well, does it have any x-intercept? No. Does it have y-intercept? Yes, if I put a 0 here, it would be 4 over what? Negative 1, which is negative 4. So y-intercept is 1, 2, 3, 4, right there. Okay? So let's go to graph it. How do we graph it? We go to the vertical asymptote and think of numbers to the right of 1, right? So let's approach them this way. So what's the number to the right of 1? Close to it. Let's say 1.1, right? So we know the graph is either here or here because this is a vertical asymptote. But the question is, where is it? Is it here or there? Well, let's see. 1.1. We're going to put 1.1 in here and see what we get. 4 over 1.1 minus 1. What is it? Is it a positive number or negative number? Well, looks like it's a positive number because 1.1 minus 1 is 0.1 and 4 divided by 0.1 is a positive number. So it's going to go that way, right? Now, it's got no other place to go but go what? Approach this. So it looks like the graph is going to approach this line right there. Now, what about to the left of 1? Come up with a number to the left of 1, close to it. Let's say 0.9, right? And then we substitute 0.9 in the function. Now, so remember this was what? This was positive. What about this? Well, 0.9 minus 1 is negative 0.1, and then for positive over negative, it would be negative. So that means to the left of this line, the function is here. Where does it have to go? Well, it has to cross the y-intercept and has to approach its asymptote. And that's the graph of what? 4 over x minus 1. That's how it's graphed. Okay. So let's do another one. What about number 12? This one. Well, in this one, again, vertical asymptote. Does it have vertical asymptote? Yes. X squared minus 9 equal to 0. So that means x squared equals to 9. That means x is plus and minus 3. Now, those numbers don't make the numerator 0. That means this graph has what? 2 vertical asymptotes, right? Now, what about the horizontal asymptote? Well, numerator's degree is smaller, so y equal to 0 is a horizontal asymptote, right? And what about x-intercept? Well, the x-intercept is a number that makes what? The numerator 0, so it's x equal to 0. Not the denominator, only the numerator, and that's the x-intercept. What about the y-intercept? Well, the y-intercept is when you substitute 0 here, you get what? You get 0. So 0, 0 is the y-intercept. So if you graph this, you're going to see like, so 1, 2, 3, that's what? 1 vertical asymptote, and 1, 2, 3 is another vertical asymptote. X-intercept is at 0, y-intercept is also at 0, right? So that's the same. Now we have to decide where this function is. We know it has to be up here or down here, or up here or down here, or up here or down here, right? So where? Let's just start from here. We know this is 3, this is negative 3. So pick a number close to 3 on the right. Let's say 3.1. Now, if you want to make the calculations easier, arithmetic. Now, we don't want to graph this with the calculator. We just want to do arithmetic with the calculator. So we use the same trick that we used in the previous video. So what we do, we put this function in y1. So that's x squared minus 9. And then we just want to use the table feature. So make sure this is on ask, and then we go to table. Let's get rid of that. Let's put 3.1 in there. Is it a positive number or negative? Looks like it's positive. So that means the graph is where? The graph is over here, right? And the horizontal asymptote was actually the x-axis itself, right? So this is over here, has no place to go but what? Go there. Now, one thing we need to check before we continue is, does it cross its own horizontal asymptote? Again, if you do that, if you set this equal to its own asymptote, which is this right here, you get cross multiply, you get x equals to 0, right? So that means it crosses its own asymptote over here, right? So that's the crossing point for asymptote, horizontal asymptote, and it's right there. Okay, what about to the left of 3? So let's pick a number to the left of 3 with the calculator. What's a good number to the left of 3? Well, 2.9. So let's put 2.9 there. Negative, so that means it's over here, right? So the graph is over here. Where does it have to go? Well, it has to come over here and cross the x and y intercepts. Now I'm going to come over here and see what's going to happen here. Well, what's going to happen here is we have to pick a number to the right of negative 3, which is negative 2.9. Looks like it is I put 2.9. I meant negative 2.9. All right, so that's positive. That means on this side right here, this goes up this way. So it's going to go that way and cross and approach that. To the left of negative 3, we put negative 3.1. And that's negative. That means the graph is over here and has no place to go but what? That way. Right? So that's the graph of this rational function. Okay, so let's do another one. Let's do number 20 maybe. See if we can find one. Number 20 here. So here again, find the x and the y intercept for this one. We're going to find everything for it. So let's do everything for this problem. So vertical asymptote. Does it have any vertical asymptote? No. Why not? Because x squared plus 4 cannot be 0 with real numbers. Because then x squared equals to negative 4, and this has no real solution, right? That means there is no vertical asymptote, right? Now, what about x-intercept? Well, the x-intercept is when the numerator is 0. So x equals to negative 5 is the x-intercept. What about the y-intercept? Y-intercept is when we put 0 here, 0 here, we get what? 5 over 4, right? And what about asymptotes? Horizontal asymptote, does it have any? Yes, y equals to 0. How do we know? The numerator's degree is 1, denominator's degree is 2, right? Again, we can graph this, but we just graph similar one. So I'm not going to graph it. I'm just going to continue and do another, maybe do another one. So 22, we could do that. X and y intercepts. You set the numerator equal to 0. You find the x intercepts and y intercepts. But I'm going to do number, let's see, 26. Let's do one. 26, okay. Again, what's the vertical asymptote? Well, x minus 6 equals to 0, so what? X equals to 6, right? And what is x-intercept? Intercept would be what? Would be 2x equals to 0, so x equals to 0. And then what about the horizontal asymptote? Y equals to what? 2 over 1, which is 2. Why? Because they have the same degrees. So horizontal asymptote is 2 divided by 1. The leading coefficient over the leading coefficient. Okay? And the y-intercept is, well, put 0 here, 0 here, you get 0. Right? Alright. Now, sometimes, like for example, in this example here, let me see if I can find one. So, do 36 maybe? We do 36. So here you go. So now let's look at these two examples. Now, sometimes if you see a rational function like that, it might be related to what? 1 over x or 1 over x squared. Now, obviously, this doesn't look like transformations of 1 over x, but if you divide, so let's see, this one looks like transformation of this, right? So you start with 1 over x, then you move it horizontally to the left, and then down 1 unit, right? So you can graph this easily this way. Think of what this looks like, right? For 1 over x, the horizontal asymptote is y equal to 0, and the vertical asymptote is x equal to 0. Now what have we done here? Let's get 2 points on the 2. Let's say 1, 1. And then this one is negative 1, 1. So we can use transformations to graph this. How? Well, remember, how do we deal with transformations, right? So if you think of the original graph g of x, right? That one. Forget about this for now. So that one. So if you have a and g of a here, what do the transformations do to the point on the graph? Well, we know it's going to take that into what? It's going to subtract 3 from x and subtract 1 from y, right? So subtract 3 from x, so that's a minus 3, and subtract 1 from y, right? So let's graph this. First of all, where does y equal to 0 go? Which is horizontal asymptote. Well, we say we have to subtract 1 from y. It doesn't have x, so it's just y. What's 0 minus 1? Y equals to what? Negative 1. So y equals to negative 1 becomes the horizontal asymptote of this. So let's see. 1. So here's horizontal asymptote, right? What happens to x equal to 0? Well, x minus 3, so 0 minus 3 is negative 3. So go to 1, 2, 3. And here we go. Right? Okay, and what happens with 1, 1? Well, 1, 1 goes to 1 minus 3 is negative 2. 1 minus 1 is 0. So negative 2, 0. Negative 2, 0. Right here. Right? That's where it goes, right? And where does negative 1, 1 go? Negative 1, 1 goes to, what's negative 1 minus 3? Negative 4. And what's 1 minus 1? 0. So negative 4, 0. So that's negative 4, 0 right there. Right? So it looks like, look at the shape here. So it looks like what we have is, it's going to approach that, and this is going to approach that, right? And over here, look at the shape, right? So it's going to what? So my, so negative 1, negative 4, and then negative 1, 1 is going to go to negative 1, 0. Okay, so it goes there. 1, negative 1, negative 2, negative 3, and negative 4. So subtract from x we did, and then subtract 1 from y, we got negative 4, 0. Okay, now let's see what happens here. Are we over here or are we over there? So this number is what? Negative 1, negative 2, negative 3. So let's pick a number to the left of negative 3, which is negative 3.1. So if I put negative 3.1, what do I get here? I get what? Negative 3, negative 3.1 plus 1 would be negative 0.1. 1 over negative 0.1 would be a negative number. Negative minus negative is negative. So it's going to be over here, right? And then so this is going to approach like that, right? So ouch. Oh, my fault here. I'm seeing my mistake. That's a negative 1, not negative 1, 1. Here we go. So there you go. So that negative 1 minus 1 would be negative 2. So this point is in the wrong place. Let me fix that. Here you go. So it would be negative 4 and what? And negative 2. So negative 2 is about, remember this was negative 1, so it's about right here. All right, there you go. We got it. So notice that we could have done this without the transformations, but we could also do it using transformations, right? So let me fix that too. That was a negative 1. I put 1 there. So everything else is correct. Yes. Okay. Now, we could have, of course, think of this as what? As just a regular rational functions and do it. But it would be easier probably if you do what? With transformation. Now, what about this one? Does this look like that is related to this 1 over x? Well, let's see. What we can do is divide x plus 2 by what? By x plus 3. Now remember, there is a negative here. We're going to keep it. So what is it when we divide? Well, we know how to divide. We could do a long division. So x divided by x is 1. 1 times x plus 3 is x plus 3. Then we change the sign and add. So this x and this cancels. So negative 3 plus 2 is negative 1. And we stop, right? So what do we write? Remember there was a negative here, right? So it's going to be negative whatever we get here for that, which is what? Which is 1 plus the what? The remainder divided by that. Negative 1 divided by what? X plus 3, right? And if I multiply by this negative, what do I get? I get negative 1. This is a negative here. Plus what? 1 over x plus 3. But notice, that's the same thing that we were working on. They don't look the same, but they are the same, right? So when you have a linear over a linear, when you divide it, you get something that is related to what? Those two functions, the function that we already know how to graph, and we can use transformations to graph it. All right. Okay, and looks like this video got longer than I expected, so I'm gonna do a few more and then maybe do another video. All right, so let me do 41 something that. Where is it? 41 here, 40, and this is 41. Okay, so what does this look like? Well, again, we can think of, you could use the procedures that we talked about to graph it, vertical, asymptote, horizontal, and all that. But we know this function, right? This function looks like what? Looks like this. Right? So the horizontal asymptote is 0, y equals to 0, and vertical asymptote is also x equals to 0. Now we can put a point here now. This is 1, 1, and this one is, this time is correct actually, it's negative 1, 1, okay? All right, now, is this related to that? Yes. It looks like first we take what? We move it to the right 2 units, and then what? Let's stretch it by 4, right? So moving to the right, so if we start with this as g of x, then if I have a point a, g of a on that, what happens to it under this transformation? Well, we have to add 2 to x. Remember, opposite, inverse of this happens to the points. So add 2 to x, and then multiply y by 4. 4 times what? G of a. So if you want to graph this, we say, okay, what happens to y equals to 0? Y equals to 0, we have to multiply it by 4. 4 times 0 is still 0. So that means horizontal asymptote doesn't go anywhere, right? Horizontal asymptote stays here. What happens to x equals to 0? Well, we have to add 2 to it because that's x. So that goes to what? Goes to there. That's the vertical asymptote. Remember, this is 2. Okay? Now, what happens to 1, 1? Well, remember, we have to add 2 to x. So I will call 3 and multiply y by 4. It goes to 3, 4. 3 and 1, 2, 3, 4. It goes over here, right? And what happens to negative 1, 1? Well, remember, negative 1 plus 2 is 1, and 1 times 4 is 4. So it goes to 1, 4. 1. Negative 1, 1, that's correct, okay, plus 2, and then multiply by 4. So it's negative 1 and 4 right there, right? So, so basically what happens here, we want to also figure out whether it crosses its own asymptote or not. So what do? We have to set this equal to what? Its own asymptote, which is 0. And again, we see that's not possible because we get 0 equals to 4. That means no solution, right? So it doesn't cross its own asymptote. So we know that this is going to go that way, right? And this is going to come down and approach that for sure. And over here, what is the y-intercept? Does it have a y-intercept? Well, let's see. The y-intercept looks like is, well, not here, because that's for this function. Let's do it here. So the y-intercept is going to be, if I put a 0 here, 0 minus 2 is minus 2. Squared is 4. 4 over 4, 1. So that means it has a y-intercept of 1, right? Where am I? Oh, wait a minute. This is -1 and 1. I put -1 and 1 goes to 1. Oh, I'm in the wrong place. Put it at -1. Goes to 1 and 4. Here we go. Ah, that's 2 mistakes I made on this video. Alright, so it goes to 1 and 4, not -1 and 4, right? 1 and 4. Okay, so we know the y-intercept is 1, right? So again, this 1, 1 goes to 3, 4. We have that right there. And then -1, 1 to 1, 4 goes to 1, 4 right there. So what happens is that this goes to, it has to approach the asymptote, goes to here, and then approaches the horizontal asymptote, like that. Oh, it's going to look a little bit better if you graph it with a calculator. So basically it looks like that, the same shape, with just different place, right? Alright, so that's 41. And then we can, let's see if we can graph another one. One more for you, but I want to do it, I want to do my own example so I can show you what happens if you have what? If you have a slant asymptote. So let me give you an example. So let's say we have f of x equals to x to the third minus 1 divided by x squared plus 2. So this, let's make it something that minus 1, minus 4, here we go. That's good. Okay, so does it have vertical asymptote? Yes. X squared 4 equals to 0, so x is what? Plus and minus 2. Does it have a horizontal asymptote? No, because the degree of the numerator is bigger. Does it have a slant asymptote? Yes. What is the slant asymptote? Well, we're going to have to divide this x to the third minus 1 by what? By x to the second minus 4, right? So this divided by that is x, and multiply, we get x to the third minus 4x. Change the sign and add, so we get 4x minus 1, right? And we stop because 4x minus 1 is there. You can't divide anymore. So y equals to x is what? Is the slant asymptote. And what is the x-intercept? Well, x-intercept, we're looking for only real numbers, so just use what? That x to the third is 1, and so x is going to be 1, right? And now we can look at the graphs. Graph it with you'll delete that one and delete that one as well, and delete that one as well. So I'm going to graph it like that. So let's see, y equals to x to the third minus 1, and then divided by x to the second minus 4. There. And I'm going to graph y equals to x to show you that that is exactly what we talked about. You see, that has a slant asymptote, right? And the shape of it, and has two vertical asymptote at 2 and -2. You see, this is one right here, and here's another one over here. Okay, so I'm gonna say let's end this video now, and I'm gonna see you in the next video. Okay, so take care.